So I would like to introduce the org committee of tinyML group in Ukraine. So I'm Oleg Boguslavsky. I'm today's moderator. I'm co-owner and CTO of Data Science US. We provide software development services with a specialization in the field of AI and machine learning. So we'll be happy to work with everyone who might be interested in these services. So you can visit our website for more information. And our second member of the committee is Sergey Kashenko. He is interim CEO at Yellow. It's a very cool crypto solution. So together, this is the first webinar which we held this year, and we are happy that it has a lot of attention and a lot of participants. And now I'm happy to introduce to you Andrii Polukhin, our speaker. The main areas of Andrei's interests are the research of deep learning architectures and methods of training deep networks. He's interested in all the mathematical aspects and theorems behind it and in the interaction of AI with the surrounding world. He has a lot of practical experience in putting the models on the edge. So I'm confident that today's presentation will be very interesting, and it has a huge amount of slides. Hope we'll be on time, but we'll see. So I'm passing the word to Andrii, and once again, thanks everyone for joining tinyML webinars and stay with our community. Andrii, your turn now.
Yeah, hi all. Thank you, Oleg, for presentation. I will continue. Let me speak a little bit about myself. So I'm ML engineer in Data Science UI and Samba TV. I'm also doing mentorship in Projector Institute in Ukraine and also in 1011. Also, I'm getting a master's degree in mathematics, and I'm writing about the AI in my Telegram blog. Also, I have my personal website where I also post some useful articles about the latest machine learning researches and technologies. So I'm very passionate about the artificial intelligence, and today I would like to speak about the lightweight neural network architectures. Before we continue, I would like to say that today there are a common practice to stack more layers and get more data, and then you get the better model. But our resources is limited. So, for example, if you would like to put the artificial intelligence in a mobile system or edge device, maybe TV, so we need to reduce the size of the model. We need to optimize it. And so this is how to do it. The structure of this talk is the following. There are 9 points. We will describe the problem overall. Then we will describe the optimization pipeline steps. And also I conducted the huge research about the modern mobile architectures. I created the taxonomy of these architectures. There are MobileNet, model scaling formula, neural architecture search, group convolution family, and also Squeeze-and-Excitation family. And more, there is also a VIT family. So let's start. The first one is, 1 minute, I can see the title of the screen. Oh, okay. The first one is a problem statement. So the larger model produces better results but runs slower. And also smaller model produces worse results but runs faster. So how can we make the optimal choice between the size and the performance of our model? Here's 3 main steps to optimize your machine learning model. The first one, and it is a lecture objective, the main topic of this webinar is a model selection. It is the step in your development when you need to select your model. You can select MobileNet, which is very popular architecture. You can select FBNet, or maybe you will go to VIT architectures that is more efficient nowadays, and so on. There are thousands of different architectures. The second step is a model optimization. You could change the model architecture, like you can do pruning, you can do low rank factorization, distillation, singular value decomposition, weight clustering, so on, so on. It is about changing the model architecture. You could not change the model architecture, but anyway optimize it with quantization, for example. You could also combine the methods above and get the best results. And the last step is a non-model optimization. It is a software and hardware optimization. Software is about software accelerators like DeepX, CN, and like we are talking about the machine learning frameworks. For example, you could write the custom shaders for TensorFlow or PyTorch and so on. Talking about the hardware, we're talking about the microcontrollers like electronics that could optimize the inference of your model, maybe even training. Commonly it's maybe most about the CPU devices, but about GPU also, low power. So let's start from the families, deep learning architecture families. There is a MobileNet family. It's MobileNet V1, V2, and V3. Then we will go to the model scaling formula families. It's about EfficientNet and tinyNet. Not everyone heard about tinyNet, but tinyNet is a special formula for EfficientNet for mobile devices. Neural architecture search is the next family. It's about the brute forcing or more intelligent search of the optimal architecture of the models. Then we will overuse the group convolution family. We will be talking about ShuffleNet, ShuffleNet V2, CondensedNet, MixedNet, GhostNet, and the other ones. The next family is Squeeze-and-Excitation. We'll be talking about SqueezeNet, SqueezeNext, and Squeeze-and-Excitation network, the basic one. And the last one, we will shortly overuse the VIT mobile architectures. We will be talking about mobile VIT, the Apple publication and architecture, and HVIT's architecture. So let's start from the MobileNet family. There are three versions of the MobileNet. MobileNet architecture was developed by the Google. The first version was developed in 2017. So what is special about this architecture? So the first one, the authors removed the common convolution operator and inserted depth-wise separable convolution. Also, they replaced ReLU with ReLU 6, and they introduced width and resolution hyperparameters that you can fine-tune for your needs. Here is an architecture of the depth-wise separable convolution. You need to separate your common convolution operator into the two separate operators, where one will be operating in depth-wise spectrum, like width and height. And the next one is point-wise convolution that will connect the separate features together and do element-wise multiplication and sum up in the end. Also about replacing ReLU with ReLU 6. So ReLU 6 is more optimal for low-power devices because your low-power devices could handle a very tiny bits of information. So for ReLU 6, you only need a few bits of information because ReLU 6 could contain the values from only 0 to 6, no more, no less. Also, speaking about hyperparameters, there are width and resolution multiplier, which could tune your size of the network to your business needs. The next architecture is MobileNet V2. It's 30% faster and 1% accurate than the first version of MobileNet. It's also the model from the Google. So authors replaced the nonlinear bottleneck with linear bottleneck. They invented inverted residual blocks and provided expansion projection way. Here's a residual connection and inverted residual connection. So the common residual connection is simply addition of the input information input features to the output features. So you could save the valuable information from the beginning and pass it to the end of your network. Inverted residual convolution is a little bit more trickier. Like the thing is that they removed the non-linearity. They provide the only linear operation here, and like some changes in passing the features through these layers. And here's a conception of expansion projection. The expansion projection works like zip and unzip. So the expansion layer acts as a decompressor like unzip that first restores the data to its full form. So mapping into the high dimensional space, then the depth-wise layer performs whatever, like filtering with convolutions, and like it's filtering the more important features, and then projection layer compresses the data back to the small representation of your information. The next version is MobileNet V3. It was invented in 2019. It was 2 times faster than the previous version. It was 30% smaller, but maybe a little bit accurate, less accurate than the previous one. So the authors replaced ReLU 6 with hard switch that is more optimal for mobile architectures. They introduced Squeeze-and-Excitation model. They used MNAS-Net and NetAdapt algorithms to find the optimal number of layers and features, and they redesigned the expensive layers. Speaking about the H-switch function, so it's simply the multiplying of x with ReLU 6 from x plus 3 divided by 6. It's more curative function than it was before. Like here's a comparison of switch and H-switch and sigmoid and H-sigmoid. Squeeze-and-Excitation block was invented in Squeeze-and-Excitation network that we will be talking later about. But the main concept is the following one. So firstly, for any given transformation f, you need to map your input x to the feature maps, and then you do convolution that will transform your data into the 1 times times number of channels, while your main feature information will pass through the network, and in the end they will do multiplying one element from the 1 by 1 bytes by the entire feature layer of the produced features. So it's simply feature calibration model. And here's some changes in architecture of the building block. For comparison, here's V2 and V3. They inserted Squeeze-and-Excitation model and also replaced activation functions with H function, like sigmoid with H sigmoid. So to sum up, the first version of MobileNet was 10 times faster and smaller than VGG 16. The second version was a little bit faster and smaller than the previous one, and even a little bit more accurate. And the third version was 2 times faster than the second one, 30 times smaller, but a little bit less accurate. I personally used mobile nets a lot in my business needs, in my work, because there are a lot of implementations in different frameworks of mobile nets. There are a lot of optimized, pruned, quantized, distilled architectures of mobile nets, so we can easily use it in our production systems for image classification, for object detection, and the other tasks. So it's the easiest, the basics one architecture. The next interesting approach is model scaling formula family. So background, what is width, depth, and resolution? Here you can see the pipeline of the neural network. And there are some comparison of width, depth, and resolution. So as you can see, the depth is number of layers in your network. The resolution is input resolution of the, for example, image and the size of your features inside the network. And the width is number of features per layer. Like, for example, you have a convolution operator with 16 kernels or maybe 64. So it's width difference between them. And how can we find the optimal number of width, height, and width, depth, and resolution? So to help us with it, there are three architectures: EfficientNet V1, EfficientNet V2, and tinyNet. EfficientNet V1 architecture was 6 times faster than ResNet and gpipe by Google. They invented the special model scaling formula, so they didn't guess hyperparameters. They use alpha times beta in square times gamma in square, approximately equals 2. So using this equation, you could calculate your parameters. The second version of EfficientNet was EfficientNet V2, and it was 2 times faster than the first version. What was the changes? Firstly, they used progressive training with, instead of static training parameters. What it means? For example, when you train your image classifier, you could start from training it on 64 per 64 images. Then you will increase the resolution of the input image. You will use 128 by 128. Then you will twice increase the resolution, so on, so on. So it's progressive training. You could also do it in the opposite direction, like reduce the resolution, or you can, I don't know, do something like sinusoidal resolution. So it will make your model more robust to the input images. The second point is using depth-wise layers in later stages, because the authors prove that depth-wise layers in early stages are not very efficient, like convolutions, but they are very efficient in later stages. So why don't we just remove them in the early layers and use only in the later stages? Like, we can't remove them entirely, we can reduce the number of filters, for example. And also they used fused MB convolution instead of MB convolution. Fused MB convolution is simply a union of the convolution 1 by 1 and depth-wise convolution 3 by 3. Also, they applied neural architecture search to fine-tune the hyperparameters of the architecture and scaling. And the interesting one, maybe not everyone heard about it, so it's tinyNet. It was invented in 2020. tinyNet was 2% more accurate than EfficientNet V1. But the interesting thing is that the authors also provided the formula for hyperparameters, but this formula is efficient for a low number of your layers, because EfficientNet was designed for big models. So you can scale your model bigger and bigger, but it will still be efficient. But when you will try to apply EfficientNet formula for V0, V-1, V-2 architectures, it would not be efficient. But tinyNet formula is efficient. This formula was developed by mathematical approaches based on Gaussian process. So it's really effective. To sum up model scaling family, EfficientNet V1 was 6 times faster than ResNet. Awesome. The second version was 2 times faster than the first one version. And the tinyNet was designed specifically for mobile architectures. Until we continue, maybe it's time to make some questions. What do you think, Oleg?
Yeah, so if there are, I mean, I don't see any questions in the Q&A so far, so I assume that all good, but just a reminder to everyone, so if you have questions, you can post them immediately to the Q&A, and then once we'll accumulate a certain amount of questions, we'll stop and answer the questions and then resume the presentation. So, Andrea, I assume that you can, given that there are no questions as of now, there was one question which I addressed myself, but other than that, you can just continue. Oh, there is one question. So the question is, do you think this can be run on platforms like STM32 or Raspberry Pi?
Yeah, if we are talking about MobileNet architectures, they are very popular, and there are implementation for ARM devices, for Raspberry Pi. I personally saw the distilled versions of the Raspberry Pi that can run like 10 FPS on Raspberry Pi. Of course, with small resolution in input, but anyway, it can run. It can be run. It's about MobileNet. About EfficientNet, it's also very popular architecture, but tinyNet, for example, more specific one. So maybe to develop the tinyNet to edge device, it would require more time to develop this architecture and train and fine tune.
Okay, and there is one more question. Can federated learning be applied to these frameworks?
Oh, I don't know. I don't know the answer. Sorry, really can't answer.
Yeah, I think that we can just try to answer offline. There is also one question: can it be run on Arduino?
Oh, maybe, yeah, for Arduino, it's more specific platform than Raspberry Pi. So maybe it would be even more harder to find, for example, EfficientNet. I'm not sure that there are open sourced versions of MobileNet for Arduino, but I think for MobileNet, there are implementations, but not for EfficientNet.
Okay, so the next question is, have you tried any of these models on audio mode? I'm not sure what is that. Audio mode.
Sorry, can you please specify more details? What is it? Thank you for that.
Yeah, maybe you can just rephrase the question. So next question is, can these models be quantized for optimization?
Yeah, sure. I saw the blog post in internet where the guy took MobileNet architecture and like did really a lot of quantization, like int8 or something like this. So it was a lot of FPS with this architecture. I didn't saw quantization with EfficientNet, but I'm pretty sure that there are some ready-to-use EfficientNet architectures.
Okay, thank you, Andrei. Next question is, we are talking about tinyML model to be used in the training phase or in the inference phase?
We are talking specifically for inference. It's not about the training. For the training on edge devices, there are more specific techniques to do it. We're talking, this lecture is only about the inference of the tiny models on the edge devices. So it's about architectures that are running fast and efficient.
Okay. I think the next question is simple. I'll answer it offline. Are these architectures free to use and or be modified for commercial purposes, or there are any licensing limitations?
Like I'm working in machine learning for more than 3 years, but I haven't seen any of the publication that describes some architectures that you could not implement in the practice. Like maybe there are some architectures, but these popular architectures like MobileNet and EfficientNet are 100% could be used in production. The only thing that you need to rewrite the code, for example, if the authors provide the original code of their research, you could not use it in production. You need to change it. You need to write it from scratch by your hands, and so it will work.
Okay, and the last question for before Andrii will resume the presentation. So the question is: presented architectures and benchmarks are based on the problems with the image as an input. How would that translate to other domains of problems and inputs, like, for instance, audio, acceleration, and similar sensors?
Mm-hmm. Interesting question, thank you. MobileNet architecture is interesting because of the depth-wise separable convolution. So you can use depth-wise separable convolution in 1D space or in 3D space. So you can also use depth-wise separable convolution in audio. And speaking more about it, audio is very often represented by the if I'm not wrong, spectrogram, yeah, or like when you do Fourier transformation. So it's basically the image, and with this image you can use it as a 2D data and use these architectures. About EfficientNet, yeah, maybe formula of EfficientNet is more specific for images. And I don't think that it could be applicable for audio or something other.
Okay, and also I see that the question regarding federated learning, Evgeny wrote that he would like to answer this question. Evgeny, maybe you can answer that.
Yes, I think federated learning typically requires quite a bit of more memory. So because you need to aggregate deltas from different devices on one, so it's more like a training type of problem, not an inference type of problem. So that's today. I think it's hard to do federated learning on microcontroller type of devices. You need to have bigger devices for training.
Okay, thank you. So I think that we are done with the first portion of questions. So Andrii, you are welcome to continue.
Yeah, sure. Thank you, Oleg. So let's continue. The next family is neural architecture search. So background, what is neural architecture search? This task is composed from the three main definitions. The first one is search space. So the search space is the set of architectures and building blocks that we can use to build the neural network. The search strategy is a strategy that we use to find the architecture, and the performance estimation strategy is how do we know that this architecture is optimal and is sufficient for our needs. So neural architecture search is a search of optimal neural architecture for your specific data with your specific restrictions. For example, the maximum amount of memory to use, the maximum battery consumption, the maximum CPU consumption, and temperature, and so on, so on. And there are plenty of these algorithms. Many of them constructed by evolution algorithms, many of them from genetic algorithms. Also, the people do neural optimization with these algorithms. So let's start from NASNet. It's maybe the most basic algorithm to do neural architecture search. NASNet, it is an algorithm that allow you to find the optimal architecture, and the architecture that was found was 3 times faster and 4% more accurate than Inception. Yes, Inception is old architecture, but we are talking about 2017 year. And for that times, it was a really good result. So authors used a NASNet cell-based search space and scheduled draw path regularization technique. NASNet search space is constructed by two basic cells, normal cell and reduction cell. The only two cells that are composed in a predefined way, and the objective of the algorithm is to find the structure of these two cells, so we will find the optimal architecture. The scheduled draw path regularization technique means that as long as you do search, the more probability of the dropping of some evolution path of your blocks. So the longer your pipeline of the evolution of your network, the most probability that it will be dropped. So the model will optimize the architecture. The next one is PNAS-net, the same year, but 8 times faster and 5 times efficient than NAS-net. How did they do it? They use sequential model-based optimization instead of reinforcement learning and evolution algorithms. So yeah, you can do like a meta learning. You can learn the model architecture that you will teach to do some task. It's a more newest and modern approach to find the architecture, because evolution algorithms was invented really a long time ago, and reinforcement learning also. Also, there is a ChumNet algorithm, not architecture. It allows us to gain 8% of accuracy more than ResNet 50 with the same latency. So Chameleon is basically adaptive genetic algorithm where the gen is a vector of hyperparameters, the number of filters in your convolution operators, and locations of your bottlenecks. You need to define your optimization strategy, and then this algorithm will optimize your architecture for your data, platform, energy, latency, and so on and so on. The next one is MNAS-net, a very popular algorithm to do neural architecture search. Nowadays, it produced 2 times faster architecture than MobileNet V3 and NAS-net. The main point of this publication was to minimize latency directly instead of minimize flops to reduce latency, because measuring latency directly is really expensive, because you need to, as you can see in this image, you need to train your model, you need to evaluate it on the mobile device, measure the latency, measure the latency, do backpropagation optimization, and optimize your architecture. It's really very expensive comparing with measuring the flops. Like you need to only measure the number of operations that you
Seems Andrii is frozen. Can somebody write in the chat? Did you also lose Andrii? Okay, sorry for that. So maybe some technical issue. So we'll be let's wait a few minutes. He should go. Okay, Andrii is back. So
yeah, I'm very sorry. There are problems with lightning in Ukraine, so we do the best that we can, but sometimes. So Can you hear me? Can you see the screen?
Yes, everything is good. So let's go ahead.
Okay, yeah. So let's continue. FBNet. This algorithm is also neural architecture search, and it did 420 times faster search than MobileNet. How did they do it? They use differentiable neural architecture search framework. So you use gradient descent optimization to optimize your architecture directly without computing like latency or flops or something like that. You just compute the gradient relatively to latency, for example, and optimize your architecture. The next one is MobileNet, the same year, a few times faster search than common reinforcement learning search. Instead of using reinforcement learning search, you could do agent evolution. Agent evolution means that at the early stages of the search, you do evolution, and then you will not do evolution, you just train your model, something like this. So to sum up, there are a lot of algorithms for neural architecture search. They all different based on evolution, on gradient descent, on reinforcement learning. Some of them specific for convolution-based networks, some of them for maybe transformers, and so on, so on. The really cool result, as I see, is FBNet. Really 420x faster search than MobileNet. It's awesome. The next family is group convolution family. What is group convolution? So the basic convolution operation is using a few kernels to compute the pairwise multiplication of the elements, and then you sum it up into the output features. But what if we will not sum up all of the elements in a feature? Like you will split your elements into the groups, and your convolution will perform summing only in this group. It requires less operations, but as you can see, it could be less efficient because you reduce the capacity of your network to learn the connections between the elements, so your accuracy could drop. But some people invented methods that could really perform even better with group convolutions, or at least not very bad, not very worse. The first one is CondenseNet, 2017 year. This architecture was 2 times smaller than ShuffleNet. They used weights pruning in the early stages of training, only at the early stages, and then they fine-tuned the model. Also, they used group convolutions instead of convolutions. And the interesting thing is that they did not predefine the groups of convolutions, like 3, 4, 5 groups, but they learn this grouping automatically during the training. So they used optimal grouping location between the elements. Let's inspect it in more details. So here's a few condensing stages of your optimization. There are C-1 condensing stages if you choose the condensing factor C, for example. With G equals 3 groups, and condensing factor C equals 3, we will do 2 condensing stages. At each stage, we will remove 1 divided by C filters. And at the end of this pipeline, there still will be 1 divided by C features remaining. And then we will rearrange these features in the optimal way, so there will be no like friction multiplications by 0, for example, when you do something like pruning, it will be optimal operation for your device with very really less operations with nearly equal performance. On the right side, you can see the image of training loss relative to the epochs. We can really clearly see three condensing stages, and then the increasing of the loss when we do recalibration of the features, rearranging. But then the loss value really goes down. The next architecture is ShuffleNet V1. It was 13 times faster than AlexNet. Yeah, AlexNet is very old architecture, but anyway, this research from 2017. It was plus 7% more accurate than MobileNet V1. The thing is, they used group convolution with feature shuffling. So yes, you do group convolution, so you reduce the number of operations, but you will shuffle your features connections between the groups. So abstractly, you use all the connections, but with some gaps. So the number of operations is less, but the performance is nearly the same. Here's a building block of this ShuffleNet architecture. It's called ShuffleNet unit, and it looks like this. There is a residual connection, and there is a shuffling. Shuffling goes after the one-by-one group convolution, and at the end you concatenate the. No, sorry, it's not a residual connection. It's residual. It's residual connection because in the second version of ShuffleNet it will be just split in the features, but in the first one it's residual connection. So you concatenate the input features, you concatenate the resultant features, you perform the ReLU and output the features. And there is a second version of the ShuffleNet. It was 58% faster than MobileNet V2 of the same year of development and 63% faster than ShuffleNet V1. How did they do it? They used channel shuffle at the end of the block instead of the beginning of the block. They used ReLU before the concatenation of these features, and they split features in two groups before the convolution, the identity features and features that you will process with your operations. Also, the interesting architecture is a MixNet. MixNet was 4% more accurate than MobileNet V2. The authors used mixed convolution, and the idea is very simple. You take convolutions of the different sizes. So instead of using 3 by 3 10 times, you use 3 by 3, 5 by 5, 7 by 7, so on, so on. And you use group convolution with it. So you reduce the number of operations, but you increase the kernel. But anyway, the flops is smaller, but the result is nearly the same as without grouping. The interesting architecture is HostNet. It's 1% more accurate than MobileNet V3, but the idea is really tricky. Like you use depth-wise convolutions to produce the host features. You apply your host convolution. So let's inspect it visually. So here is our input data. Then we process this data with convolutions, and we have this size of features. Then for each feature, we apply the simple depth-wise convolution one time, and we get the new feature map. And then we just stack these two groups of convolution outputs. So we get twice more features with a very cheap depth-wise convolution, and it really works. It really reduces the number of operations. So without all the overhead that was invented at MobileNet V3, we just simply do tricky depth-wise convolution and get the same, even better results than MobileNet V3. The next interesting architecture is DiceNet. DiceNet was 3% more accurate than MobileNet V2 and ShuffleNet V2, and they invented a really interesting unit, Dice unit. It's called dice unit. So you use 3 different convolutions. First convolution is performing depth-wise inference. The second one is width-wise, and the last one is height-wise. And in the end, you stack these features. Like even not stack, you do like product, like including to card product, something like this of these features. It's not stacking. Then you process these features with convolution one by one, do some residual connection, some convolution operations, average pruning, and so on and so on. And in the end, you will achieve a really representative feature vector with a very cheap operation, because these 3 convolutions are cheaper than the only one big convolution, because it's factorization of the convolution operation. Another factorization architecture is MicroNet. MicroNet was 2 times smaller and 3 times faster than MobileNet V3. They used microfactorized group convolution, and with instead of ReLU, they used dynamic shift max. There are a lot of materials to get into the microfactorized group convolution, but we can expect the microfactorized depth-wise convolution. So there is a factorization of the point-wise and depth-wise convolutions. Depth-wise convolution is very simple factorization, because you know every possible matrix you could produce with multiplication of 2 vectors. For example, for my matrix k by k, you could multiply vectors k by 1 and y by k. So instead of using convolution with filter k by k, you use 2 convolutions, k by 1 and 1 by k. So it's the right image. And you really reduce the number of operations a lot. There were, computational expensive. So it was O from k square c, and they reduced the number of operations to O from kc, really divided by k. So for example, if you are using convolution 3 by 3 with macrofactorized group convolution, you will reduce number of operations in 3 times. And dynamic shift max is a special activation function for such group convolution architectures. You take the maximum from the circular group shifts of your layer. So you take all the possible outputs in your grouped architecture, like circular group, and take the maximum of it. So you will source the relevant information. Sorry. To sum up, CondensNet was 13 times faster than AlexNet. CondensNet was 2 times smaller than ShuffleNet. ShuffleNet V2 was even 63% faster than ShuffleNet V1. And MixNet, GhostNet. So in practice, I personally used ShuffleNets. I used GhostNets and MixNet. The interesting thing is that all these tricks with group convolution are very interesting mathematical and in theoretical space, but when you do all these things in practice, they really very common don't work, because the common 3 by 3 convolution is very optimized for the devices, specifically for GPU inference, but for CPU also. So when you try to factorize your convolution, or you apply convolutions like in MixNet 3 by 3, 5 by 5, 7 by 7, and more, these convolutions are not optimal for the inference in the modern frameworks like PyTorch, TensorFlow, and so on. And the performance is not following the theoretical results. But this architecture is really efficient, they're really small, so you can start from them, and then if you really need them be efficient in your device, you can rewrite the shaders, write custom CUDA kernels for those architectures, and I believe they will be very, very efficient. Okay, I can continue, or we can...
Yeah. I think, Andrii, it's better to continue to cover two more families of neural networks, and then we'll finalize with the Q&A session.
Okay. Squeeze-and-Excitation family. Squeeze-and-Excitation family based on Squeeze-and-Excitation approach. There are only three architectures. So the first one is SqueezeNet. SqueezeNet use FIRE model. This architecture is 50 times smaller than AlexNet. FIRE model is maybe early invention of the depth-wise separable convolution. It's not depth-wise separable convolution, but I think depth-wise separable convolution was inspired by SqueezeNet, because it also consists squeeze and expand 1 by 1 filters and 3 by 3 convolution filters, but it's not depth-wise separable convolution. The next architecture is SqueezeNext, the improved version of the SqueezeNet. It was the year when the MobileNet V1 and V2 was publicated, so the authors knew about the MobileNet depth-wise separable convolutions, so they used it. And also they add residual connections. So the difference between the MobileNet and SqueezeNext is maybe only in the architecture, but building blocks are the same. And the results are nearly the same with MobileNet V1, but a little bit more faster, and a lot more faster than the first version. Squeeze-and-Excitation network, the basic network that invented the Squeeze-and-Excitation blocks that we were talking before when we talked about MobileNet architectures. To sum up, I use Squeeze-and-Excitation block in my architectures. This idea is simple and really efficient. It will save you a lot of operations. And that's all, because depth-wise separable convolution was invented before the SqueezeNext. So yeah. The last family that I would like to talk about is mobile transformers. We'll talk about Mobile VAT by Apple and HVATs. So Mobile VAT was invented in the past, in the last year, in 2022. It was 3% more accurate than MobileNet V3 and 6% more accurate than DIT transformer architecture. They used Mobile VAT block instead of combination of convolutions and attentions. Here is a picture how does Mobile VAT block works. So in the bottom line, you can see all the pipeline. So the input image followed by the convolution operation. Then here's a MobileNet V2 block, simple MobileNet V2 block with depth with separable convolutions, residual connection, inverted residual connections, and so on. So they just decreased the resolution. And in some point, when the resolution is 32 by 32, they applied Mobile VAT block. And then they applied it even 2 times more. Mobile VAT block is simply convolution plus VAT. You just unfold your features into the linear layers. You do L times of transformer, then you fold your data, you do convolution, you do residual connection, you do convolution and by N, and you output the features. And then again, MobileNet V2 block, Mobile VAT, MobileNet V2. In the end, there is a convolution 1 by 1, global pooling, and linear layer. So that's simply the architecture. I don't think it's very, I tested it in my work, and it's not very fast because the idea is cool, but optimization of the transformers in edge devices is really a problem nowadays, I think, because this is a new technique. There are a lot of implementations, but it's not so optimal as, for example, convolutions. And edge VITs, the same year, 2022, is 12% more accurate than mobile VAT. The main result of this publication is local global information exchange bottleneck. It includes aggregation information from the neighbor tokens with depth-wise convolution. sparse delegate tokens for long-range information exchange, and transposed convolutions to update information since tokens. Here's a global diagram of this architecture. The input features goes through the patch embeddings and then local. There is 4 stages: first, second, third, and fourth one. All of them are the same. They are just reducing the resolution of your features. And here's their architecture. There is local aggregation, sparse attention, and local propagation models. How does they work? Local aggregation model looks at the nearest tokens of the image when you unfold your image, and it tries to learn the information between the neighbor patches, but from outside into the inside information, into the inside tokens. Global sparse attention is doing global attention, like it took a very long range tokens and tried to learn the dependency between them. And local propagation is like an inverse to local aggregation. It learns the dependency of the inside features to the outside features. It really looks like a simple convolution, but in context of transformers when you unfold your data. As I said, I tried mobile V8 in my projects. It's really hard to train transformer architectures. It's really hard to optimize them. Even for GPUs, your custom transformer layers are really heavy, and even more for mobile architectures. But I believe that the future is with transformer architectures, and we will do really good optimization for these layers. That's all from me. Thank you for attention. I'm open to your questions.
Yeah, thanks a lot, Andrii. And let's go through the questions. I'm not sure this is the question to you. So there is a question regarding the audio signal processing. So audio classification and audio event detection, which algorithm would you recommend?
For audio detection, which architecture would I recommend?
Yeah, for audio classification and audio event detection.
Like, I think maybe this person means about efficient architecture for audio recognition. So I really recommend to use some of these architectures that I was talking about. Yes, these architectures for 2D information, for images. But if we are talking about the convolutions, you could anytime you can do 1D convolution, you can try to rearrange these approaches for your audio data, and I think it will perform really good.
Okay. Next question is let's start from the beginning. So do you have a look at MorphNet in order to only get a network size which is really necessary and not larger?
MorphNet?
Mm-hmm.
No, I didn't heard about MorphNet. It's really interesting. What is the year of the publication of this architecture? I will read about it. I don't know about it.
Okay, there is also the request a little bit more details about CharmNet. Maybe you can back to the slide and maybe provide a little bit more details. CharmNet.
CharmNet.
CharmNet. Mm-hmm.
CharmNet. It's a basic neural architecture search algorithms that use adaptive genetic algorithms, where your gene that will mutate and you will find the optimal gene. So your goal of optimization is your hyperparameters of your features. So the main idea is that it uses genetic algorithm for vector of your hyperparameters. And your evolution strategy optimize accuracy, latency, energy, and the other goals that you will possess.
Okay, thanks, Andrei. We'll try to be as fast as possible because we are already out of time. Many people had to join to other meetings. So next question is, NAS can be applied to any ML algorithm or only, let's say, to convolutional neural networks? NAS, yeah.
Yes. Yeah, sure. NESNet is just an approach to do neural architecture search. So you need to define two cells, normal and reduction. Of course, there is some difference between them. You could read as more details in the original paper. So you need to define these two cells. You will locate them in specific order in your architecture, and your algorithm, NASNet, will optimize this architecture for your purposes, for audio data, for video data, for text maybe, so on and so on.
Yeah, thanks, Andrei. So next question is essentially the question is whether there is some kind of good paper which compares all these architectures in terms of accuracy, speed, weight. So I mean, to like kind of the paper similar to your presentation, but even more in depth. So maybe you heard about some paper like that.
Yeah, I really I looked at those papers, I read them partially. I get information from them because there are maybe a few surveys of the mobile device architectures, but they all look at different aspects. Like, for example, some papers looks at the speed, some at the performance. Of course, I can share these papers with you if Oleg will provide some communication channel for us.
Yeah, I think that the main communication channel will be tinyML forum, so where the presentation will be shared as well. So I think that that's where it will be possible to make further discussion.
I will share. Yeah, I will share.
Okay. So the next question is, when you said these architectures, could you give us some use cases like which are used for object detection, segmentation, or post-estimation, or 3D SLAM respectively? What work are you focusing on? Do you use GANs or diffusion models or VA? Computer vision is converging with NLP. What are your thoughts about text to video and generative models? So a lot of questions from one person. Maybe you can address some from that.
Mm-hmm. Okay, so model optimization, model selection, this architecture development, really efficient for simple tasks like image classification, even for object detection. But for such tasks as generative art, for example, like generational models, these tasks are very sensitive to your architecture. So when you will try to optimize your gun, for example, it's really times harder than simple image classifier, because in generative models, when you remove at least one filter, the results could be really very different because all the stages depends on the previous ones. So I think the half of these techniques will not work for some generation models, for example, because some models really require a lot of computations and you could not really simplify them. I think for optimization such of the models, there are some tricks of reparameterization, of quantization, for example, half precision. Maybe you could optimize your software or hardware, but for such a sensitive task, for example, generation, for example, style gun 3, I don't know. You can replace some convolution operation with something like a group mixnet or micronet. Maybe it will work.
Okay, thank you. Next question. Some comments about fine-tuning on device in supervised settings. It's challenging to provide supervision for streaming data. So it's rather comment than a question. What are your thoughts on that?
Oh, can you repeat, please?
So that's a question from Renam Silva. So he said that it's challenging to provide supervision for streaming data. So how do you fine tune on device in supervised settings? I mean,
It's question more about training the model on each devices. And you could not speed up training with selection of optimal architecture. Like optimization of training on each devices, it's a question of software and hardware optimizations, not architecture, because your architecture is fixed. And when you train, you could only freeze some parameters to not waste your computations on them. So maybe you could optimize your training on device with freezing the most non-valuable parameters. For example, if you know that some part of your network did not produce really very valuable output and you can prune half of the parameters, maybe you should not include this part of the into the training parameters, and you will save some computation resources.
Okay, thanks, Andrei. Next question: how non-model optimization using FPGA can be useful and implemented for AI training on the edge?
FPGA?
Yeah.
No, unfortunately, I don't know what is FPGA.
Yeah, FPGA, it's how to say, I mean, I know what it is, but programmable gate, I don't remember what this abbreviation means, but it's a kind of programmable logic. So it's like somewhere in between ASICs and fixed function accelerators. So it's like programmable logic. So, but anyway, I assume you did not deal with that. So I don't know that. Yeah. So next question is, computer vision is converging with NLP. What are your thoughts on that?
Yeah, I also see these trends too. It's all because of the large language models, ChatGPT, when Jan LeCun said that, oh, people stop, these language models is just a probabilistic models without real knowledge of the outside world. So I think it's the question of the time, like stability. I created the stable diffusion hyped for a few months, and now it's time for ChatGPT. Maybe after the Microsoft Square half of the OpenAI, maybe the things will change. Yeah, but I think that stable diffusion, for example, is more accessible for communities than something models like ChatGPT, for example, because large language models are very large. To inference a large NLP model, you need really a lot of resources, and that's why OpenAI provide on the online interface. But for generative art, you could really run stable diffusion on your 3090 GPU, and I believe that we will see a lot of interesting use cases of the generative art, but I think it will be a few with large language models because it's less accessible for community.
Okay, thank you. And probably the last question for today. So the question is: tinyML is using tinyML generator, uses TensorFlow model, if I'm not wrong. Can you please let me know how to use tinyML generator, another tool for PyTorch model? Again, if you did not deal with tinyML generator, probably won't be able to respond, and I'm not sure that whether someone else can help with that.
Yeah, unfortunately, I cannot help with it.
Okay. Some suggestions about papers if I want to train text to video in terms of avatar talking to you.
take a look at the first order motion model and the second version of it. Also take a look at some researchers from Adobe and NVIDIA. They are developing talking heads with the text. And it's mostly the task of lip sync when you have an input signal of audio or even text, and you need to map this text into the human's lips. So it's lip sync tasks, just Google it. There are a lot of publications around it. And I saw a lot of open source solutions for such tasks.
Okay, thank you very much. I think that we are done with the questions, and now I need to go back to the presentation for a few more minutes. And let me try. Yeah, seems like. Okay. I need to go back to the end of the presentation, and first of all, thanks everyone for joining. Thanks a lot for asking all these questions, and of course we really appreciate tinyML strategic partners, and big thanks for supporting the community. And I would like to mention about our executive strategic partners, Edge Impulse, Qualcomm, Syntiant, our platinum strategic partners, DeepLight, Krikatech, Renesas, Sony, our gold strategic partners, Analog Devices, ARM, PhotoHub, Microsoft, NXP, SensiML, ST Microelectronics, Synaptics, and our silver strategic partners, Arduino, AIZip, AON Devices, GreenWave Technologies, Groovit Incorporated, IBM, ImageMob, Itemeres, Note AI, OctoML, Prophecy, Kixo, Rixen, SAP, Schneider Electric, Silicon Labs, StreamAnalyze, TDK. Thanks a lot to all our partners. And once again, big thanks to all participants. Big thanks to Andrii, to our speaker, and we hope to see you again during our upcoming events. So thank you very much, and have a very great day or evening or good night. Thank you very much.